Right now, hundreds of galaxy clusters are racing through space at 2 million mph towards something we cannot see. The observable universe shows us 93 billion light-years of reality, but that's just a speck compared to what lies beyond. Out there, universes bubble into existence, cosmic strings slice through reality, and structures beyond imagination wait in the darkness. This is what lies on the other side of our universe. The number 93 billion represents how wide our observable universe stretches. But here's the paradox. The universe began only 13.8 billion years ago. Light travels at the ultimate speed limit, so how can we see objects 93 billion light-years away when light has only had 13.8 billion years to reach us? The answer reveals everything. Space itself has been expanding. When light left a distant galaxy 13 billion years ago, that galaxy was much closer. But during those billions of years, space expanded and carried that galaxy farther away. Today it sits 93 billion light-years from Earth, even though its light shows how it looked when it was only a few billion light-years away. This expansion created our cosmic bubble, containing roughly 2 trillion galaxies. Everything else remains hidden behind a barrier made of time itself. Light from regions beyond simply hasn't had enough time to cross the expanding space and reach us yet. Our 93 billion light-year bubble represents just a tiny fraction of what exists. Think of standing on a beach, seeing 20 miles of ocean, knowing vast continents exist beyond that horizon. Somewhere past our cosmic horizon, billions of galaxies continue their dance around black holes. Stellar nurseries birth new stars, and potentially, regions of space follow completely different rules of physics. Space continues expanding. Every second, distant regions race away faster than light can travel. We'll never see them. The 93 billion light-year limit isn't a wall, it's a window showing only the nearest room in an infinite cosmic mansion. 380,000 years after the Big Bang, the universe caught fire. The entire cosmos blazed with light so intense that nothing could escape. Every photon bounced endlessly between particles of matter. Space itself glowed white-hot at temperatures exceeding 10,000 degrees. Light couldn't travel more than a few feet. The universe was completely opaque. Then everything changed. As space expanded and cooled, electrons finally stuck to atomic nuclei. For the first time, complete atoms formed. Light suddenly broke free and began streaming across the universe. This moment released a brilliant flash in every direction simultaneously. Scientists call this the surface of last scattering. These photons still travel through space today as the cosmic microwave background radiation. This radiation surrounds us like a glowing shell, marking the absolute limit of what any telescope can ever see. Anything before 380,000 years after the Big Bang remains forever hidden behind this wall of fire. The cosmic microwave background looks almost perfectly uniform in every direction. Regions of space that were never close enough to exchange heat somehow ended up at exactly the same temperature. This uniformity proves that something extraordinary occurred before the wall formed, pointing toward the infinite cosmos beyond our reach. Count every galaxy visible through the most powerful telescopes, and you'll hit 2 trillion. Each contains hundreds of billions of stars. Yet this incomprehensible collection represents essentially nothing compared to what lies beyond. If you move 93 billion light-years in any direction from Earth, you'd reach the edge of our observable bubble. From that location, you could observe a completely different sphere of space 93 billion light-years wide. An alien astronomer there would see roughly 2 trillion galaxies we cannot see from Earth. Scientists studying the cosmic microwave background have confirmed that space appears flat on the largest scales. A flat universe extending beyond our observable horizon has a specific implication. The total universe is either infinite or unimaginably larger than what we can see. If infinite, then infinite galaxies exist beyond our view. Somewhere beyond our cosmic horizon, galaxies identical to the Milky Way orbit supermassive black holes. Planets exactly like Earth circle stars exactly like our Sun. The same physical processes that created our solar system have repeated countless times in regions we'll never observe. Galaxies at the edge of our observable universe move away at nearly the speed of light. Galaxies just beyond our cosmic horizon recede faster than light can travel. We'll never see them. The cosmic expansion acts like a one-way mirror. Every second, thousands of galaxies slip beyond our cosmic horizon forever. However, something from beyond that horizon is reaching back and pulling our galaxies toward the darkness. Galaxy clusters shouldn't be moving in the same direction. According to cosmic expansion, clusters should spread apart uniformly. Instead, hundreds of galaxy clusters are streaming through space at over 2 million mph toward the same region of sky. This mass migration spans billions of light-years and shows no sign of slowing. Alexander Kashlinsky and his team named this phenomenon dark flow. Researchers calculated how much gravitational attraction would be needed to pull galaxy clusters at such speeds. Nothing in our observable universe contains enough mass. All the galaxies, dark matter, and supermassive black holes we can detect combined couldn't generate the required force. The source must lie beyond the edge of observable space. Dark flow shows galaxy clusters moving in response to gravitational forces we cannot see. What could be massive enough? The leading theory involves structures that formed during cosmic inflation, enormous concentrations of matter pushed beyond our cosmic horizon. These structures could contain the mass of millions of galaxy clusters, compressed into regions larger than our entire visible cosmos. Some scientists propose stranger explanations. The dark flow could result from gravitational effects leaking through from parallel universes, or it might be evidence of cosmic strings, one-dimensional defects in spacetime that stretch across the multiverse. If dark flow is real, something unimaginably massive lurks beyond our sight, and that same cosmic realm might bear permanent scars from collisions with neighboring universes. Deep in the constellation Eridanus, space has a bruise. This cosmic injury spans 1.8 billion light-years and appears as a cold spot in the cosmic microwave background radiation. The region contains roughly 100 times less matter than it should, as if something reached through reality and scooped out a massive chunk of the early universe. The cosmic microwave background should show only tiny temperature variations. The cold spot violates this rule by displaying a temperature deficit so large that random chance could never explain it. The most exotic explanation involves bubble universe collisions. According to eternal inflation theory, our universe formed as a bubble of spacetime that stopped inflating, while the surrounding multiverse continued expanding. Other bubbles formed nearby, and occasionally two bubbles collided before their walls hardened into separate realities. A collision between our universe and a neighboring bubble would create exactly the type of temperature anomaly we observe. Computer simulations predict we should see circular patterns in the cosmic microwave background if our universe experienced such impacts. In 2010, scientists thought they had found 4 circular patterns matching predicted collision signatures. However, statistical analysis suggested these could result from random chance. The cold spot remains one of the most puzzling features in cosmic microwave background maps. Whether it results from bubble universe collisions, exotic physics, or unknown cosmic structures, its existence proves our understanding of the early universe remains incomplete. Nothing can travel faster than light, except the very fabric of reality. During cosmic inflation immediately after the Big Bang, space expanded exponentially. In less than 1 second, regions grew by factors of 10 to the power of 26 or more. A region smaller than a proton inflated to the size of a basketball or larger, much faster than light could travel. Galaxies don't move through space faster than light. Instead, space itself stretches and carries galaxies along. This distinction allows cosmic expansion to violate the speed limit without breaking physics laws. During inflation, regions that were once close enough to exchange light and heat suddenly found themselves separated by distances larger than light could cross. This explains why the cosmic microwave background appears so uniform. Before inflation, the entire observable universe was smaller than a grain of sand. Every part could reach the same temperature. After inflation, these regions became causally disconnected. Today, cosmic expansion continues accelerating. Galaxy clusters beyond a certain distance recede faster than light. We can still see some because their light left billions of years ago when they were closer. However, any light they emit today will never reach Earth. This creates a cosmic event horizon currently about 16 billion light-years away. Inflation didn't end everywhere simultaneously. Picture the early universe as a vast ocean of space expanding exponentially. This ocean contained the inflattened field that drove expansion. In random patches, the inflattened field began to decay. When it decayed in our region, inflation stopped. The enormous energy converted into matter and radiation, creating the hot dense plasma that eventually cooled into everything we observe today. However, the inflattened field didn't decay everywhere. In most regions, inflation continues today. Within this eternally inflating background, new bubbles randomly stop inflating and convert their energy into matter. Our universe is one of these bubbles floating in an eternally boiling cosmic pot. Once inflation starts, it becomes eternal. The inflattened field creates new space faster than it can decay. Even though countless bubbles form every second, they occupy only an infinitesimally small fraction of the total volume. Most of space remains inflating forever. This eternal inflation produces an infinite multiverse of bubble universes. Each bubble forms with its own Big Bang, evolves its own galaxies and stars, and eventually dies. Meanwhile, the background space continues creating new bubbles for eternity. Most bubbles remain forever separated by regions of eternally inflating space. However, occasionally two bubbles form close enough that their walls touch before the space between them inflates too much. When that happens, universes collide with consequences that ripple through both realities. Reality splits billions of times per second at the smallest scale. Zoom into any patch of empty space at distances smaller than the Planck length, about 10 to the negative 35 meters. At this scale, spacetime dissolves into churning quantum foam. Virtual particles pop into existence and annihilate in time, frames shorter than any clock can measure. This quantum foam drives the creation of entire universes. During inflation, quantum fluctuations in the inflattened field determined when different regions would stop inflating and form bubble universes. These fluctuations are completely random and happen everywhere throughout the eternally expanding multiverse. Each second, countless quantum fluctuations spawn new bubble universes throughout the infinite multiverse. Each undergoes its own Big Bang, develops its own physical laws, and evolves its own cosmic structures. If quantum fluctuations spawn infinite bubble universes, then every possible set of physical laws must exist somewhere. Bubbles where gravity repels, universes where electromagnetism works in reverse, realities where time flows backward or in multiple directions. The anthropic principle suggests we observe a universe hospitable to life simply because we couldn't exist in sterile alternatives. Out of infinite possibilities, conscious observers can only emerge in rare bubbles where conditions allow complexity. This means identical copies of you exist in bubble universes with nearly identical histories. When universes crash into each other, both realities remember. During eternal inflation, bubble universes form randomly. Most remain forever separated. However, when two bubbles nucleate close enough together, their expanding walls eventually meet. The collision creates gravitational waves that propagate through both bubble universes. These waves carry specific signatures and leave permanent imprints in each universe's cosmic microwave background radiation. When our bubble universe collided with a neighbor, the gravitational waves would have reached the surface of Mars, scattering, creating temperature fluctuations with a very specific pattern, circular rings centered on the impact direction. Matthew Johnson and his team developed computer simulations predicting exactly what collision signatures should look like. In 2010, researchers announced 4 potential collision signatures in cosmic microwave background data. However, follow-up analysis from the European Space Agency's Planck satellite suggested these were likely statistical flukes. Finding definitive evidence of bubble collisions would prove our universe is part of a vast multiverse and that other realities exist beyond our cosmic horizon. The search continues with increasingly sophisticated methods. Every bubble universe forms with its own randomly determined set of physical laws. The strength of gravity, the mass of particles, the speed of light, and electromagnetic force intensity all get selected from a vast range of possibilities during bubble nucleation. Most combinations produce sterile universes. Imagine a universe where gravity is 10 times stronger. Stars would burn through their fuel in millions of years instead of billions. Stellar explosions would sterilize entire galaxies with radiation. Complex chemistry couldn't develop. Alternatively, consider a bubble where gravity is 10,000 times weaker. Matter would never clump together to form stars. No nuclear fusion, no heavy elements, no planets, no life. Make electromagnetism slightly stronger and atomic nuclei fly apart. Make it weaker and electrons spiral into atomic nuclei, eliminating chemistry. Some bubble universes develop with entirely different particle physics. Particles that attract in our universe might repel in theirs. Forces that decay over distance here might strengthen with separation there. The most exotic possibilities involve universes with different numbers of spatial dimensions. We live with 3 dimensions of space plus 1 of time. Other bubbles might evolve with 4, 5, 10, or hundreds of spatial dimensions. String theory suggests bubble universes with different numbers of compact dimensions might be common. The anthropic principle suggests most bubble universes remain sterile, while only a tiny fraction develop conditions suitable for complexity and consciousness. However, our bubble universe might not be limited to exotic physics beyond our horizon. Some theories predict reality-bending objects exist right here. While black holes devour everything that comes close, white holes would represent the opposite phenomenon. These theoretical objects expel matter and energy so violently that nothing can approach their surfaces. The mathematics that predict black holes also predict white holes. Einstein's equations describe how massive objects curve spacetime. Solutions show matter falling inward toward a singularity, and matter exploding outward from a central point that nothing can reach. White holes might explain some of the most energetic phenomena in the observable universe. Gamma-ray bursts release more energy in seconds than our sun will produce in its entire lifetime. Quasars shine with the brightness of a trillion stars. However, a white hole would be fundamentally unstable in our universe. Any material approaching would prevent it from expelling matter. The white hole would immediately collapse into a black hole. Some cosmologists propose the Big Bang itself was a white hole event. Our entire observable universe might have erupted from a single point in higher dimensional space. The most speculative theories suggest black holes in our universe might connect to white holes in other realities, creating cosmic tunnels linking separate regions of the multiverse. Imagine a crack in reality so thin you could never see it, yet so massive that 1 inch would outweigh Mount Everest. These cosmic strings might stretch across the entire observable universe as one-dimensional defects in spacetime. They formed during the first fraction of a second after the Big Bang, when the universe underwent rapid phase transitions. Think of water freezing into ice. As liquid water cools, cracks sometimes form between different crystal regions. The early universe experienced similar phase transitions. Cosmic strings formed along boundaries where different regions developed different properties. Each string would measure no wider than a proton, yet contain incredible density. A single mile would weigh more than Earth. The gravitational field would be intense enough to bend light and distort time. Cosmic strings are topological defects. You can't destroy them without fundamentally altering spacetime itself. They persist as permanent scars, marking the violent birth of our universe. Cosmic strings would be incredibly long. The shortest would span from one edge of the observable universe to the other. Most would extend far beyond our cosmic horizon. Some might form closed loops smaller than galaxies, while others could connect our bubble universe to neighboring realities. The motion of cosmic strings creates gravitational waves. As strings vibrate, oscillate, and intersect, they generate ripples in spacetime detectable by instruments like LIGO. The nanograv collaboration measures tiny timing variations in pulsars. Recent data shows patterns that could result from gravitational waves produced by cosmic string networks. If cosmic strings connect our bubble universe to other realities, they might allow limited information transfer between separate cosmos. Finding cosmic strings would prove that reality contains structures stretching through dimensions we're only beginning to understand. Two black holes spinning in perfect synchronization could tear a tunnel through reality itself. Mathematical solutions to Einstein's equations predict that under specific conditions, extreme spacetime curvature could create shortcuts between distant regions. Scientists call these wormholes. You'd need two electrically charged black holes positioned at precisely the right distance. The charges must be perfectly balanced. Then you'd need cosmic strings to serve as cosmic scaffolding, holding the wormhole tunnel open. The resulting structure would create a stable tunnel connecting 2 points in spacetime. Travel time through the tunnel would be essentially zero. If cosmic strings formed during inflation, they could stretch from one bubble universe to another. A wormhole constructed using these interbubble strings would create a direct connection between separate realities. Imagine stepping through such a tunnel and emerging in a universe with completely different physics. Even theoretical wormholes face severe stability problems. The cosmic strings holding them open would gradually lose energy through gravitational wave radiation. Most models predict complete collapse within microseconds. However, some frameworks suggest quantum effects or exotic matter with negative energy could stabilize wormholes for longer periods. If stable wormholes exist, they would solve the cosmic isolation problem created by faster-than-light expansion. Bubble universes normally forever separated could maintain communication and travel links through wormhole networks, creating a cosmic internet connecting multiple realities. For every second that ticks forward in our universe, a second ticks backward in its mirror twin. This mirror reality formed at the exact same moment during the Big Bang. Both realities share the same starting point, but evolve in opposite temporal directions. The concept emerges from fundamental symmetries in physics. Most physical laws work equally well whether time moves forward or backward. However, the second law of thermodynamics breaks this symmetry. Entropy always increases over time in our universe. Sean Carroll and other cosmologists proposed the Big Bang created two universes with opposite entropy arrows. In our universe, entropy increases as time moves forward. In the mirror universe, entropy increases as time moves backward relative to our temporal reference frame. Both universes start with low entropy at the Big Bang moment and evolve toward higher entropy states. The mirror universe would contain antimatter instead of ordinary matter. Antistars would shine just as brightly and follow the same nuclear fusion processes. Antiplanets would orbit antistars in solar systems identical to ours from a distance. If intelligent life evolved in the mirror universe, those beings would experience their reality as completely normal while considering our matter-based universe exotic. The mirror universe theory explains the apparent absence of antimatter in our observable universe and provides a natural explanation for time's arrow. Some scientists speculate that dark matter in our universe might actually be ordinary matter from the mirror universe. Gravitational forces could link both realities, while electromagnetic interactions remain separate. Most people imagine space as flat, extending in straight lines like an infinite sheet of paper. However, the overall shape of space depends on the total amount of matter and energy it contains. Our universe appears to have flat geometry on the largest scales, but other bubble universes could develop with completely different spatial geometries. Imagine a universe with negative curvature where space bends outward like a hyperbolic saddle. Parallel lines would gradually diverge. Triangles would have angles adding up to less than 180 degrees. Navigation would be profoundly disorienting. Objects appearing to move in straight lines would actually follow curved trajectories. In flat space, matter clumps together under gravitational attraction to form stars, galaxies, and clusters. Negative curvature would work against this gravitational clustering by constantly stretching distances. Galaxies would have difficulty maintaining their structure. Star systems would be less stable because orbital mechanics would follow hyperbolic paths. Some theoretical models suggest regions of negative curvature might exist within our own universe on scales smaller than we can detect. These hyperbolic zones could be left over from cosmic inflation. Negative curvature could also exist in extra-spatial dimensions. String theory predicts reality might contain 6 additional spatial dimensions, curled up so tightly they appear as points from our three-dimensional perspective. While you read this sentence, trillions of new universes began existing. The cosmic inflation that created our bubble universe never actually ended. It continues throughout the infinite multiverse, constantly stretching space and spawning new realities at an accelerating rate. The inflattened field exists everywhere and drives exponential expansion. Quantum fluctuations randomly push this field above and below its average value. When fluctuations push the field below a critical threshold, inflation stops in that region. The field's energy converts into matter and radiation, creating a hot Big Bang. Meanwhile, inflation continues in surrounding regions. The volume of inflating space grows exponentially, creating more locations where quantum fluctuations can trigger new bubble formation. Each second, the total volume multiplies by factors of 10 raised to enormous powers. Within this explosively growing volume, quantum fluctuations create new bubble universes at incomprehensible rates. Each bubble universe lives and dies in cosmic isolation. Once formed, surrounding space inflates away at faster-than-light speeds. The bubble cannot send signals to other bubbles or receive information from the wider multiverse. Each reality evolves independently according to its own randomly determined physical laws. However, eternal inflation ensures that every possible combination of physics eventually gets realized somewhere. Universes with 10 spatial dimensions, realities where time branches in multiple directions. The machine also produces exact copies of our universe with identical histories. Quantum mechanics limits the number of possible arrangements for matter in any finite volume. With infinite bubble universes, identical copies become mathematically inevitable. Movement in 10-dimensional space would drive you insane within seconds. We live trapped in 3 spatial dimensions: length, width, and height. Your brain evolved to navigate only 3 dimensions of space plus 1 of time. String theory demands that reality contains at least 10 dimensions total. 6 additional spatial dimensions exist, curled up so tightly at every point in space that we cannot detect them directly. Other bubble universes could develop with these extra dimensions unrolled to macroscopic sizes. Imagine a reality where objects can move in 10 full spatial dimensions instead of just 3. A sphere in 10-dimensional space would appear in our universe as mysteriously changing 3-dimensional cross-sections. The complete object would remain invisible because most of its volume extends through dimensions we cannot perceive. Beings native to 10-dimensional space would have sensory organs detecting light, sound, and matter from directions that don't exist in our reality. They could approach you from dimensional angles that would make them appear to materialize from nowhere and vanish into nothingness. Gravity would spread its influence across 10 dimensions instead of 3, making it much weaker over any given distance. Stars might not form because gravity couldn't overcome thermal pressure. However, other forces might become dominant. Electromagnetic interactions, or exotic forces predicted by string theory, could shape matter into structures we cannot imagine. Some string theorists propose our 3-dimensional universe exists as a membrane floating in higher dimensional space called the bulk. Other membranes could exist parallel to ours, separated by tiny distances through extra dimensions while remaining billions of light-years apart in our familiar 3-dimensional space. Gravitational forces can propagate through all dimensions, meaning massive objects in parallel universes could influence matter in our reality. This might explain some of the missing mass astronomers attribute to dark matter. Empty space weighs more than all the matter in the observable universe. What we call empty vacuum actually seethes with virtual particles that pop into existence and disappear, in time, frames shorter than any measurement can detect. These quantum fluctuations create background energy, filling every cubic inch of space. According to theoretical calculations, if you added up all the virtual particle energy in a volume the size of a coffee cup, the total would exceed the mass energy of all visible stars and galaxies combined. This quantum vacuum energy should create a gravitational field strong enough to curve spacetime into a tiny ball. Our universe should have collapsed before the first atoms could form. Instead, we observe a nearly flat universe expanding for almost 14 billion years. Something must be cancelling out the vacuum energy. Scientists call this the cosmological constant problem. Different bubble universes could have different relationships between quantum vacuum energy and spacetime curvature. In some realities, vacuum energy might remain uncancelled, creating universes that immediately collapse. Other bubbles might develop with negative vacuum energy, causing space to expand even faster. The most interesting possibility involves bubble universes where quantum vacuum energy fluctuates randomly throughout space and time. Regions with positive vacuum energy would curve space inward like invisible black holes. Regions with negative vacuum energy would curve space outward like cosmic antigravity wells. Matter would follow bizarre trajectories, navigating through spacetime regions with constantly changing gravitational properties. Some theoretical physicists propose that consciousness might influence quantum vacuum fluctuations through the observer effect. In bubble universes where this effect is stronger, intelligent beings could potentially manipulate local spacetime by focusing their awareness. This would create realities where thought directly affects physical reality and collective consciousness could reshape the fundamental properties of space itself. Every black hole in our universe might be pregnant with an entire cosmos. When a massive star collapses, it creates a region of spacetime so warped that not even light can escape. However, mathematical analysis suggests something extraordinary. The collapsing matter doesn't simply crush into an infinitely dense point. Instead, it might trigger a new Big Bang, creating an expanding universe inside the black hole. This interior universe would be completely cut off from our reality. No information can travel outward across a black hole's event horizon. From our perspective, the black hole appears frozen at the moment of collapse, but from the perspective of matter falling in, time continues normally. The collapsing material experiences extreme tidal forces. Under these conditions, spacetime itself might undergo phase transitions that trigger inflation. The interior of a black hole represents a separate region of spacetime, topologically disconnected from our universe. Lee Smolin proposed that black hole universes might explain the apparent fine-tuning of physical constants. If universes that produce more black holes also produce more offspring universes, then natural selection would favor physics that creates stars massive enough to collapse. Our universe produces billions of black holes through stellar evolution. Each could birth a pocket universe with slightly different physical laws. Over cosmic time, this reproductive process would fill the multiverse with realities optimized for black hole formation. This evolutionary cosmology suggests we live in a universe descended from countless generations of black hole ancestors. Something with the mass of 10,000 Milky Way galaxies is pulling our entire region of space toward the constellation Hydra. The Milky Way moves through space at over 1 million mph in a direction that cannot be explained by cosmic expansion alone. Our galaxy, along with thousands of neighboring galaxies, streams toward an invisible gravitational anchor located roughly 250 million light-years away. Astronomers call this the Great Attractor. When scientists point telescopes toward Hydra where this massive object should be located, they find a region that appears relatively normal. Galaxy clusters exist there, but nothing obviously massive enough to gravitationally dominate our local region. The object remains partly hidden behind the zone of avoidance, a band where dust in our own galaxy blocks our view. However, even accounting for this, observations don't reveal enough matter to explain the Great Attractor's gravitational influence. Scientists discovered the Great Attractor itself is being pulled toward an even larger structure called the Shapley supercluster. This massive collection contains the gravitational equivalent of 10 quadrillion suns. Recent mapping reveals our entire local region participates in an even grander flow toward a structure so massive that most lies beyond our observable horizon. Think of floating down a river toward a waterfall around a bend. You feel the current pulling you forward but cannot see the waterfall itself. The Great Attractor and dark flow work similarly. We measure their gravitational effects on local galaxies, but the source might extend into regions forever beyond our observation. Some cosmologists propose the Great Attractor could be a massive concentration of dark matter left over from cosmic inflation. During the inflationary epoch, quantum fluctuations might have created density variations on scales much larger than our observable universe. We observe only a small section of these cosmic megastructures. Alternative theories suggest it might be evidence of extra-dimensional physics. Massive objects existing in higher dimensions could exert gravitational influence while remaining invisible to our telescopes. Throughout our observable universe, galaxies cluster along vast filaments of invisible matter, stretching across billions of light-years. These dark matter structures form a cosmic web connecting galaxy clusters and directing the flow of ordinary matter throughout space. We map this web by observing how its gravitational influence bends light from distant galaxies. The revolutionary possibility, the cosmic web might extend beyond our observable universe into other bubble realities. If dark matter formed during cosmic inflation before bubble universes separated, then the same network of filaments could span multiple realities simultaneously. This would create physical connections between bubble universes otherwise causally isolated. Think of mycelium, underground fungal networks connecting trees in a forest. Individual trees appear separate above ground, but are actually linked through invisible root systems, allowing them to share nutrients and information. Bubble universes might be connected through similar dark matter networks. Gravitational effects could propagate along these filaments from one bubble universe to another. This might explain dark flow, where galaxy clusters appear pulled toward massive structures beyond our cosmic horizon. The dark matter web could also provide a mechanism for information transfer between realities. Gravitational waves traveling along filaments might carry encoded messages between advanced civilizations in different bubble universes. Advanced civilizations might learn to manipulate dark matter filaments as cosmic engineering. By concentrating or dispersing dark matter in specific patterns, they could alter the gravitational environment around their solar systems or create artificial connections to neighboring bubble universes. The cosmic web might serve as a transportation network for traveling between bubble realities. Consciousness might be the most powerful force in the multiverse. Quantum mechanics reveals that observation fundamentally changes reality. Before measurement, particles exist in multiple states simultaneously. The double-slit experiment shows electrons can travel through two paths at once until someone observes which path they actually took. In our universe, conscious observation appears to have minimal effect on large-scale phenomena. Quantum effects become negligible when applied to massive objects in warm environments. However, other bubble universes might develop where quantum effects remain strong at all scales. Imagine a reality where the boundary between quantum and classical physics never forms. Conscious observation could directly influence the behavior of stars, galaxies, and even spacetime itself. Intelligent beings might literally think new matter into existence or reshape cosmic structures through focused attention. If environmental decoherence never eliminates quantum superposition states, then objects of any size could exist in multiple configurations simultaneously until consciousness collapses them into specific realities. Civilizations in observer-dependent universes would develop along completely different paths. Instead of building tools to manipulate matter, they would train their minds to manipulate reality directly. Some cosmologists propose consciousness might be required for any universe to exist at all. This participatory universe hypothesis suggests realities without observers remain trapped in quantum superposition states and never develop classical properties. If correct, then bubble universes without consciousness would exist as ghostly quantum possibilities rather than concrete realities. Advanced forms of consciousness might learn to observe other bubble universes and thereby bring them into existence. By focusing awareness on specific quantum possibilities, these cosmic observers could literally create new realities through the power of attention. Your entire existence might be code running inside a computer built by beings in a higher-level reality. The simulation hypothesis proposes that what we experience as physical reality is actually a detailed digital simulation created by an advanced civilization. Every atom, every star, every thought could be computational processes in a vast cosmic computer. Any civilization that develops sufficient computational power could simulate entire universes in complete detail. If such simulations are possible, there would likely be many more simulated realities than natural ones. By pure probability, we're more likely to be living in a simulation than in base-level reality. If our universe is a simulation, then the computer running our reality exists in another universe. That universe might also be a simulation. This creates a hierarchy of realities stacked like Russian dolls, each level simulating the one below. The chain could extend through countless layers. Each level would have different computational limitations. The base-level reality would have access to full computational resources. Each simulated level would have fewer resources because some processing power must run the simulation itself. This creates a natural limit to how many simulation layers can exist. The simulation hypothesis also explains why our universe appears to have fundamental limits like the speed of light and quantized energy levels. These might be computational shortcuts built into the simulation to reduce processing requirements. Physical constants might represent resolution limits of the cosmic computer running our reality. If we are living in a simulation, we might detect glitches or artifacts revealing the computational nature of our reality. Scientists search for evidence like pixelation in spacetime at the smallest scales or computational limits in quantum system complexity. Our universe will die so that infinite others can be born. Every bubble universe follows the same cosmic life cycle: birth through inflation, evolution through expansion and cooling, then death through heat death or collapse. However, this death feeds the birth of countless new realities in an endless cycle. Here's how our bubble universe will end. Dark energy continues accelerating cosmic expansion, pushing galaxies apart at ever-increasing rates. Eventually, expansion will carry every galaxy beyond the cosmic horizon of every other galaxy. Each galaxy will become isolated, unable to see or influence any other cosmic structure. Stars will exhaust their nuclear fuel and die. White dwarfs will cool into black dwarfs. Black holes will evaporate through Hawking radiation over time periods so long that the current age of the universe represents less than an eye blink. The final state will be cold, empty space, containing only elementary particles, separated by distances larger than our current observable universe. This heat death represents maximum entropy. But the story doesn't end with cosmic death. Throughout this process, quantum fluctuations continue occurring in the vacuum. These fluctuations occasionally create regions of false vacuum, that can trigger new inflationary episodes. The death of our universe provides the quiet, low-energy environment where new cosmic seeds can germinate. Roger Penrose proposed conformal cyclic cosmology, where the heat death of our universe becomes the Big Bang of the next cosmic era. The geometry of spacetime allows the infinite future of a dying universe to connect smoothly to the birth moment of a new cosmos. Each cosmic cycle would reset the clock, while preserving certain information from the previous universe. The eternal cycle ensures cosmic evolution never truly ends. Death and birth alternate forever, with each universe's demise enabling the creation of countless new realities. This cosmic reproduction might be driven by consciousness itself. Advanced civilizations facing cosmic death might learn to encode their knowledge into quantum fluctuations that influence the formation of new universes. In this way, consciousness could achieve immortality by shaping the birth of infinite future realities. Beyond our cosmic horizon, this cycle has been repeating for eternity, creating infinite realities where every possibility becomes actual and every dream becomes real. The other side of the universe contains not just more space, but infinite versions of existence itself.